Lesson 99, the Pythagorean Theorem. Now, Pythagorean Theorem was the brainchild of a Greek mathematician named Pythagoras, or as my Hungarian grandfather used to say, Pythagoras. You must learn your Pythagoras. Now, the Pythagorean Theorem, first off, it's a theorem, which means it's been proven. Otherwise, it'd be a theory. Theories haven't been proven yet. Theorems have. So this has been proven to be absolutely true all the time, in every case where it applies. And it simply says that if we have a right triangle, and as you all well know, a right triangle is just any triangle that has a 90-degree angle in it. There's a right triangle. That if we have a right triangle, and we compare the length of the sides, that we can write an equation about them. An equation which is true. Now, when we talk about a right triangle, specifically a right triangle, this longest side here, the side that's always opposite the 90-degree angle, has a special word, special name. It is called the hypotenuse. H-Y-P-O-T-E-N-U-S-E. The hypotenuse. These other two sides are simply called the legs. Further, customarily, traditionally, we label these A, B, and C, and the hypotenuse is always labeled C. We always label that C. The other two are A and B. It doesn't matter if that's A and that's B, or that's A and that's B. It doesn't matter. I'm going to make this one A and this one B. So there's the setup. We've got a right triangle, our two legs A and B, and our hypotenuse C. So then if we consider the length of the sides, so if we take the length of A and we square it, A squared, and we add to that the length of B squared, that sum will equal the length of C squared. And this is actually fairly easy to visualize. I have here, this triangle is specifically 3 inches on this side, 4 inches on this side, and 5 inches for the hypotenuse. And I've made matching squares here. There's a 3-inch square, there's a 4-inch square, and there's a 5-inch square. So if I take A, 3 inches, and I square it, what I have is a square. And if I line that square right up against that edge there, there we go. There we go. And if I take 4 inches and I square that and I line that right up against this 4-inch edge here, there we go, right there. And if I take this 5-inch square here, line that right up against there. So I effectively square that side. I've taken the side and I've squared it. So there's a 3-inch square, a 4-inch square, and a 5-inch square. Then what Pythagoras is saying is that if we take the area of this square plus the area of this square, that should equal the area of that square. And that is demonstrably true, because this is a 3 by 3 square. That means its area is 3 by 3, or 9 square inches. This is a 4 by 4 square. That means its area is 4 times 4, or 16 square inches. And this is a 5 by 5 square. That means its area is 5 times 5, or 25 square inches. And it is certainly true that 9 plus 16 equals 25. So that's Pythagoras' theorem in a nutshell. And it's true for all right triangles. Now, if the right triangle in question has lengths that are all integer values, these are all whole numbers, there's no decimals here, then those 3 sides together, 3, 4, and 5, we call those a Pythagorean triple. So 3, 4, 5 is a Pythagorean triple. All integer lengths. And there's an infinite number of right triangles, of course. And there's an infinite number of Pythagorean triples. But some of the more popular ones, 3, 4, 5, definitely out there. What we have? We go with 5, 12, 13, because 5 squared is 25, 12 squared is 144, 25 and 144 is 169, which just so happens to be 13 squared. See, 8, 15, and 17. 8 is 64, 15 squared is 225. Together, that makes 289, which is 17 squared. So, just some of the more popular Pythagorean triples. So Pythagorean triples are just any right triangle whose sides have integer lengths. All right. Now, in addition to this 3, 4, 5, that's a very popular triangle. That shows up all the time. Right? And this 3, 4, 5 triangle, it's been known about for millennia and millennia. Even long before Pythagoras, before even the Egyptians, the Sumerians made use of a 3, 4, 5 triangle. And it's still being used today. If you are a carpenter, let's say, and you're building a deck, so you set a board up there, and then you set another board up there, and you're going to then build a frame there and then nail your deck boarding on there. You want to make sure that this is exactly a right angle. And one very common way to do that is to measure out, take your tape measure and measure out 3 feet along this edge, then measure out 4 feet along this edge, then take your measure and measure from that point to that point. And if you measure that to be exactly 5 feet, then you know that that must be a perfect square corner right there, because that would be a 3, a 4, and a 5. People have been doing that for thousands upon thousands of years. Now, in addition to the 3, 4, 5, there's 2 other right triangles that you just want to have memorized in your arsenal because they show up all the time. Now, they're not Pythagorean triples, but nonetheless, they do have a certain special property. The first of these that you want to memorize is a right triangle whose sides are 1, 1, so it's an isosceles right triangle. And then this would be the square root of 2, because, again, 1 squared is 1, plus 1 squared is 1, so 1 plus 1 is 2. So c squared, 2, square root of 2. So there's one of them there. And the other one, which you just want to memorize, just have a mental image of it ready to go at a moment's notice, is a right triangle whose sides measure 1, root 3, 2. Now, the reason why these are such useful triangles is because of their angle measures in here. The angle measures on 3, 4, 5, who cares what they are? They're ugly, like 57 point blah, 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 whatever. But these here, this is nice. The angle measures in this are 45 degrees and 45 degrees. There you go. There's your 45 degree triangle. The angle measures here, this one is 30. It's opposite the 1. And this one is 60 degrees, opposite the root 3. These triangles right here, they show up all the time. 3, 4, 5, this one, and this one. Very special triangles, worth memorizing. On the ACT, on the SAT, these show up constantly. Like they'll say, hey, little Jimmy took off from home. On his bicycle, he rode due east for 6 miles. Then he rode due south for 8 miles. How far is little Jimmy from home? Now, straight as the crow flies. Well, it would be that length right there, and you might recognize this is just a 3, 4, 5, where every side's been multiplied by 2. 2 times 3 is 6. 2 times 4 is 8. So this must be 2 times 5, or Jimmy must be 10 miles from home. There you go. So that is the Pythagorean theorem. All right. Now, let's look at the practice problems. Sketch the triangles and draw the squares on the side of the triangles as you work with problems A through C. So they want you to take this and they want you to actually draw the squares, like the red squares that I cut out on each side. So you guys can do that. That's fine. But here, we'll just use Pythagoras' theorem to find the missing side. So here we have a right triangle. So we know Pythagorean theorem applies. And the hypotenuse is 26. So here's side A. Here's side B. That's side C. So according to Pythagoras' theorem, a squared plus 24 squared equals 26 squared. All right. Well, I'm going to solve this for A. So 24 squared, I'm just going to move that over here. So I have A squared equals 26 squared. Now, because that's a positive 24 squared, I need to subtract it on this side. 24 squared. There we go. And if memory serves, 26 squared, 26 times 20, 676. 24 squared is 576. So that means that A squared is equal to 676 minus 576, which is 100, which means A is equal to the square root of 100, or 10. So A here equals 10. So there's another one of your Pythagorean triples right there. 10, 24, 26. Lovely. All right. Let's try this one here. Now, for some reason, they've chosen to name the hypotenuse B. I don't know why they would throw in that added level of trickery, because as we know, traditionally, the hypotenuse is always labeled C. But it doesn't really matter what you name it, as long as you keep it straight that the sum of the squares of the legs are equal to the square of the hypotenuse. So that means in this example here, to find the length of the hypotenuse, we simply take one of the legs, 9 squared, plus the other leg, 12 squared, and that should equal B squared, or I'm sticking with C squared in this example. So 9 squared, that's 81. 12 squared is 144. And 81 plus 144 is 225. So 225 equals C squared. That means C equals the square root of 225, which is 15. So the hypotenuse here is equal to 15. There you go. There's another Pythagorean triple. Or is it? You might also recognize straight away, without even doing all this work, that this is just a 3, 4, 5, isn't it? Where each side has been multiplied by 3. 3 times 3 is 9. 4 times 3 is 12. So 5 times 3 must be 15. So that's just a 3, 4, 5. There you go. C. Find the perimeter of this triangle right here. All right. Well, again, we don't know the hypotenuse, so we can figure that out. We will say that 6 squared plus 8 squared equals C squared. Well, 6 squared is 36. 8 squared is 64. So 36 plus 64 is C squared. That means C squared equals 100, which means C must equal 10. Look at that. C equals 10. Now, you might also recognize there that this is just a 3, 4, 5, isn't it? Where each side has been multiplied by 2. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. As I say, those three triangles, the 3, 4, 5, the 1, 1 square root of 2, and the 1, 2 root 3, they show up constantly, all the time. Now, this is not asking for the length of C. Specifically, it's asking for the perimeter of this triangle. Well, now that we know C, the perimeter is just the sum of the sides. So 8 plus 6 is 14, plus 10 is 24. So there we go. Let's finish it off and make sure we're actually answering the question. I don't know what the units. Oh, it's in feet. Sorry. So that's 24 square feet. 24 square feet. All right. So there's Pythagoras' theorem. Pretty straightforward. Pretty simple. Now, what will really help you with this is something I asked you to do like way back, one of the first couple times we ever met. And I suggested rather strenuously that everyone would be well served by memorizing the squares, at least the perfect squares, at least up through 15. And as I recall, you all applied yourself to that task with enthusiasm. So let's run through those real quick here. So 1 squared is, of course, 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared, whoops, got ahead of myself there. 10 squared is 100. Ignore that null zero right there. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. And 15 squared is 225. So you should at least have those memorized. If you want to go out to 25, that'd be great. But at least have these guys memorized right here. They'll come in real handy, working with Pythagorean theorems. And they come in handy in lesson 100, which is all about square roots and irrational numbers. Now, we've got your perfect square roots. That's what we memorized right here. So the square root of 25 is 5. Square root of 64 is 8. Square root of 121 is 11. What's 13 squared, you say? 169. But what if the square root in question is not one of these perfect squares? Well, that's the conundrum that faces us in lesson 100. So here we have a square root 7. And it says each square root below is between 2 consecutive whole numbers. Now, I don't know exactly what the square root of 7 is, and they're not asking you to find exactly what the square root of 7 is. Right? They're just asking you to figure out between which 2 consecutive whole numbers must the square root of 7 be. Well, okay. Let's look at an example here. Let's look at, say, the square root of 13. We'll get back to 7 in just a second. Now, I don't know what the square root of 13 is, but I know if I look at my perfect squares here, because 9 is less than 13, and 16 is greater than 13, that whatever the square root of 13 is, it must be between the square root of 9 and the square root of 13. Now, I could likewise say that it must be between the square root of 11 and the square root of 14 or 15. But that's not as helpful to me because I do know what the square roots of 9 and 16 are, don't I? So whatever the square root of 13 is, I know it's between the square root of 9 and between the square root of 16. And the square root of 9 is 3, and the square root of 16 is 4. Which means whatever the square root of 13 is, it's somewhere between 3 and 4. 3 point something or other. Who knows exactly what it is? I'm sure I don't. Right? So that's the plan here. We're just going to find out where the square root in question lies between two perfect squares over here, and then figure out what those two whole number answers would be. So going back to the problem set, square root of 7. Well, so I consider my perfect squares. Let's see, 4 is a perfect square. So that means the square root of 7 must be between the square root of 4 and the square root of 9. There we go. Okay, now we know what the square root of 4 is. The square root of 4 is 2. So that means whatever the square root of 7 is, it must be greater than 2. But its square root of 7 is less than the square root of 9, because 7 is less than 9. So it must be less than the square root of 9. We know the square root of 9 is 3. So whatever the square root of 7 is, it must be between 2 and 3. And you could figure out what the square root of 7 is just using a calculator or a handy-dandy slide rule. On this particular slide rule, I'm going to slide that out of the way. Just line your hairline up on 7 there. And you can read the square root off the R1 scale, right there. And that looks to be 2.64. That's what I'm saying, 2.64. And you can verify that on a handy-dandy calculator. Clear, clear, clear. 7. Oh, I have it right there. Square root 2.657, blah, 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 2.6457. There we go. But they're not asking you to find that. They just want you to find the consecutive whole numbers that that square root is between. All right. So now let's consider the square root of 70. So again, you look at your list of perfect squares, and we can see that 70 is between 64 and 81. So whatever the square root of 70 is, it must be greater than the square root of 64 and less than the square root of 81. Well, we know the square root of 64 is 8. So 8 must be less than the square root of 70, which is less than the square root of 81, which we know is 9. So whatever the square root of 70 is, it's between 8 and 9. Must be 8 point something or other. All right, C, 700. I'm saying, oh, gee willikers, I don't have these memorized anywhere up near 700. That's okay, don't worry about it. You could just get your calculator and figure it out, but we don't need a calculator because we can look at this way. 700 is the same as the square root of 7 times 100. Sure it is, because 700 is 7 times 100. Now I can split that up. In fact, I can say that that's the same as the square root of 7 times the square root of 100. Well, we know what the square root of 100 is, don't we? Yes, we do. It is 10. That means the square root of 700 is the same as saying the square root 10 times the square root of 7. Those two numbers are exactly the same, because I know the square root of 100 is 10, which means that if 7 is between 2 and 3, then 700 must be between 2 times 10 and 3 times 10. It must be between 20 and 30. And the square root of 20 is, the square of 20 is 400. The square of 30 is 900, and certainly 700 is between 400 and 900. So that's how we can just do that. We don't need a calculator. All right. Another example of working with square roots that may not be perfect squares are triangles like this one here. Okay, so 1, 1. Well, Pythagoras tells us that if I want to find what x is, then I can just take the sum of the squares of the legs. So 1 squared plus 1 squared, that should equal c squared, or in our case, x squared. So x squared equals 1 squared is 1, 1 squared is 1, 1 is 2. So x should equal the square root of 2. Well, feed me nails and call me rusty. That's one of our special triangles, isn't it? 1, 1, root 2. Huh, you don't say. Let's look at this example right here. We have 2, we have 1, and we have y, and it's a right triangle. That means Pythagoras applies. So this tells us that 1 squared plus y squared must equal 2 squared. Okay, well 1 squared is 1. I'm going to move that over there. So y squared equals 2 squared minus 1 squared, or 1. 2 squared is 4. That means y squared equals 4 minus 1, or 3. That means y squared equals 3. That means y equals the square root of 3. Well, feed me nails and call me Rusty again. That looks like our other special triangle. Yep. These two guys show up all the time. All the time. All right. So that's what they're asking you to do with your square roots. You don't have to find the actual square root. We just need to find the two whole numbers that it's between. That's all they're asking for. Or they're asking to apply Pythagoras' theorem in examples where they're not all whole numbers. They're not Pythagorean triples of some kind. All right. The other part of lesson 100 is sketching lines and approximating the locations of real numbers. Now they're focusing on irrational numbers, and we've already dealt with the difference between rationals and irrationals. Let's go over them once very quickly. Any real number is either irrational or rational. A rational number is any number that can be written as a fraction. So you give me a number like 5, that's rational because I can write it as 5 over 1. I just wrote it as a fraction. Therefore, it's rational. Okay. Of course, 1/2, 3/8, 1/8, those are all fractions. Now, another way to represent a rational number is to say that if I have a fraction and I convert the fraction to a decimal, 5 over 1 is just 5. 1/2 is 0.5. 1/3, for instance, is 0.3 repeating. Let's do 1/8. That's equal to 0.125. That if I take a fraction and convert it to a decimal, that one of two things must happen. Either it just stops like 5.5 or 0.125, or it repeats predictably like 0.3 repeating. I know that that's just going to be 3 forever. So one of those two things must happen. That is a rational number. A rational number is a number that when written as a decimal either stops or repeats predictably. Which implies that an irrational number is a number that does neither of those two things. Irrational numbers, A, you can't write them as a fraction, because if you could, they would be rational numbers. So there is no fraction that will represent an irrational number. Pi is famously an irrational number because there's no fraction that equals pi. A lot of people write 22/7. Your book uses 22/7 quite often, but that doesn't really get it. That gets you down to 3.14. And pi just goes on forever. 3.1415926, blah, blah, blah. It never stops. It never repeats. So if a number never stops and never repeats predictably, then it's an irrational number. Now, telling whether a number is rational or irrational, not always so easy, but a couple things we know for sure. First off, pi, famously irrational. And secondly, a prime number, you recall, is any number that's only divisible by 1 and itself. In other words, it has no other factors. There's nothing else that goes into 7 except for 7 and the trivial answer, which is 1. If you take the square root of any prime number, that's irrational. So in this example here, root 3, 3 is prime, so the root 3, that's irrational. 0.3, that's a decimal, but it repeats predictably, so that's rational. Pi is irrational. And minus 1/3, that's a fraction, so it's rational. So we got irrational, rational, irrational, rational. Now they're just asking you to draw a number line. And approximate the location of these on the number line. So let's see, I'll start on the lowest number here. So I'm going to start my number line off at -1. And it'd be 0. And then 1, and then 2, and 3, and 4. So there's 1, 2, 3, and 4. So there's my number line. Now I want to approximate the location of these numbers on the number line. And let's start with the smallest one, minus 1/3. Well, minus 1/3 is on the negative side of 0, and it must be 1/3 of the way from 0 to 1. So I'm going to put it right there. That's pretty close. There's minus 1/3. Splendid. Now 0.3, that's 0.3, so it's just 0.3 of the way between 0 and 1. So that would be about right there, wouldn't it? It's 1/3 of the way. 0.3 repeating. That would be right there. Root 3? Now, I don't know what the square root of 3 is, but remember what we just did up here. I know by looking at my squares that root 3 must be between root 1 and root 4. Well, root 1 is 1 and root 4 is 2. That means whatever root 3 is, it's somewhere between 1 and 2. And since 3 is closer to 4 than it is to 1, we can reasonably assert that the square root of 3 must be closer to 2 than it is to 1. So I'm going to put the square root of 3 about right there. That's not too far off. And then pi, we all know, is 3.14, blah, blah, blah. So that's going to be just the other side of 3 here. There's our good friend pi. So that's what they're asking you to do. Draw a number line and approximate the position of these numbers on your number line. So being able to tell what's rational, what's irrational. There you go. All right. Pretty straightforward, pretty simple. No concerns there. All right. Now, let's look at lesson 101. Lesson 101 is all about taking English words, sentences, and converting them to mathematical equations, or taking geometric figures and writing an equation from that figure. So when you're doing this, this is the kind of thing you encounter in story problems. There's certain words that indicate to you what's going on. For instance, 6 more. The word more, well, that almost always is going to refer to some type of addition. Product. We know that 2 factors multiplied make a product, so this is some type of multiplication going on. Okay? And the word is, well, that's an equal sign. Something is, something equals, something is. 2 plus 2 is 4. So there's some things we can look out for. So let's read this from the get. It says 6 more than the product of a number and 3. So a number. We don't know what the number is, so we need to assign it something we can refer to it. A lot of people use X. I'm going to use N. N for number. So some number says 6 more than the product of a number and 3. So the product of a number and 3 is 3 times a number. So we'll write that is 3 times N. All right. Sort of working from the back to the front. That's very typical of these type of problems. So the product of a number and 3, it says 6 more than the product of a number. So 3N plus 6. So 6 more than the product of a number and 3. There we go. Is equals 30. So now we just need to solve for N. So I'll move the 6 over here. Since it's positive, I'll make it negative. So 3N equals 30 minus 6. That means 3N equals 30 minus 6 is 24. To get N all by itself, I'm going to divide by 3, because 3 over 3 is 1. So N is equal to 24 divided by 3, which is 8. There we go. So the number that they're talking about here must be 8. Let's test that answer real quick. if I plug 8 into here, is it true that 3 times 8, which is 24, plus 6 equals 30? Why, yes, it does. 30 equals 30. So yeah, that's true. There we go. So converting English to math equations. Let's look at this one right here. 10 less than half of what number is 30? Well, we've got what number again. So I'll just use the letter n again to represent that number. N. And it says half of what number? So half of n, well, that's just 1/2 n, isn't it? Half of n. 10 less, well, less, that of course means subtraction. So 10 less than half of what number? Well, there's half of what number? 10 less than that would be 1/2 n minus 10. And it says that it is 30. Is means equals, so equals 30. All right, so let's solve for n. I'll take this 10 and just move it over there. Since it's a negative 10 here, I'll make it a positive 10 over there. So that means 1/2 n equals 30 plus 10, which is 40. Now, to get rid of this fraction, I'm not going to divide by 2. I'm going to multiply by 2 because 2 times 1/2 is 1. So multiplying both sides by 2, I get the answer n equals 40 times 2, which is 80. And let's see if that answer could possibly be correct. Quite sure it is. 1/2 of 80. Well, 1/2 of 80 is 40, and 40 minus 10 is indeed 30. There you go. So taking a phrase written in words and converting them to equations. You just do a few of those, and you'll be an old hand at it. All right. Secondly, taking a geometric figure and writing an equation from that. So let's examine this geometric figure. They want to find the measure of the smallest angle. So we want to know what this angle is here, because clearly the angle 2x must be smaller. The angle 2x must be smaller than 3x. So if I can figure out what x is, I'll be able to tell what the measure of that angle is. But how could I possibly do that? Well, we have a clue. This angle right here is 90 degrees. And this is a straight line. So a straight line is 180 degrees. That means this angle in question here, from there to there, must also be 90 degrees. So whatever 3x and 2x are, I know that if I add them together, that they're going to equal 90. So we can say 3x plus 2x equals 90. There you go. So we can add these two together because they're both just x terms. So 3x plus 2x is 5x equals 90. That means divide both sides by 5. X must be 90 divided by 5, which is 18. So x is 18. So are we done? Can we just move on? No, because it's asking for the measure of the smallest angle. Well, the smallest angle, if x is 18, the smallest angle is 2 times 18. So 2 times 18 is 36, so the measure of the smallest angle is 36 degrees. Which, just to complete this out, this angle here is 3 times 18, which is 54 degrees. And sure enough, 54 and 36 equals 90. There you go. So taking a geometric figure and writing an equation out of it. So continue. Find the measure of each angle of this triangle. Oh, okay. Well, we have a triangle. I don't know what the length of the sides are. We don't care. We're trying to find angles. I don't know what any of the angles are. But I do know this, that in any triangle, I don't care what type of triangle it is, could be a right triangle, could be isosceles, could be scalene, but any triangle, if you sum the interior angles, as you guys well know, that equals 180. So that means I can write an equation out of this that says the angle x plus the angle 2x plus the angle 3x must total to equal 180, because they're the interior angles of a triangle. So let's add these together. X plus 2x plus 3x is 1 plus 2 plus 3, which is 6x equals 180. So divide by 6. So x equals 180 divided by 6, which is 30. There you go. 30. So that means we can label all of these. If x is 30, that means this angle here is 30 degrees. This angle right here is 60 degrees. And this angle here, well, that's a right angle then, isn't it? Because 3 times 30 is 90 degrees. Cut off my legs and call me shorty. That's another one of our special triangles, isn't it? That's the 30, 60, 90. Yep, everyone laughed when old Mr. Bird said to memorize those things, but they're not laughing now. All right, well, there you go. There's lessons 99, 100, and 101. So you're ready to run off and do all those problems in those problem sets with relative ease, I'm quite sure. Now, if you're interested, if you want to stick around for a bit, they're not asking you in this problem set to find out, say, exactly what the square root of 7 is or the square root of 13. They're just asking you to find the whole numbers between there and there. But surely there must be a way to find the actual square root of 13 without using a calculator, without using, say, a slide rule. There must be some way to just do it by hand with just pencil, paper, and your own noggin. And I'm going to show you how to do that. It's kind of a fun little thing to do, I think. Yeah, and it's something very few people know how to do today because everybody uses calculators. Very few people know how to calculate square roots by hand. And there's a few methods out there, but certainly one of the best methods was a method devised by good old Isaac Newton, Newton's method. Newton's method says that if I want to find the square root of some number, capital N, that is going to be approximately equal to 1/2 times whatever n is divided by a plus a. So n is the number we're trying to find the square root of, and a is just going to be your guess. You're going to make a guess on what you think the square root is going to be. And that's where the lesson you just learned comes in real handy. So let's use Newton's method here to find out the square root of 13, a little more precisely than just saying it's somewhere between 3 and 4. So Newton's method says that the square root of 13 should be roughly equal to 1/2 times 13 divided by, now let's make a guess. We know that the square root of 13 is somewhere between 3 and 4. So I'm going to guess it's 3. So I'll just make my first guess here, 3. Plus 3. There we go. I said I'll make my first guess 3 because Newton's method here is what's called an iterative formula, which means once I get a value from this expression, if I want to get it to even further and further refinement, more and more decimal places, I can take the answer from this, plug it back into this original equation, and solve it again, and go further and further and further. So let's just start with just our initial guess, which is 3. So that would be this approximately equal to 1/2 times 13 thirds plus, I'm just going to write this a fraction, 3/1. Now, you can add those two together by finding a least common denominator and all that stuff. But we often use the butterfly method to do that in class. So let's use the butterfly method here. So 1/2, 13 thirds plus 3/1 should be 13 times 1 plus 3 times 3 all over 3 times 1. Smudged my plus sign there. The curse of the left-handed writer. 13 plus 9 is 22. So the square root of 13 is approximately equal to 1/2 times 22/3. Well, 22 is an even number, so let me cancel out that right there. So that means the square root of 13 is approximately equal to 11 thirds. Well, let's just see what is 11 thirds as a decimal. So we've got 11 divided by 3. Okay, well, 3 goes into 11 3 times, and then we're already off into decimal territory. Let me add a decimal there, add a 0. So 3 goes into 11 3 times with a remainder of 2. So let me put a 2 right there. 3 goes into 20 6 times with a remainder of 2. Okay, well, you see what's going to happen here. Let's just keep repeating. 3.66666666666. So far, we figured out that apart from just being between 3 and 4, the square root of 13 is roughly 3.66. Now, we could stop there, rest on our laurels, but let's take it one more step. Okay? So, as I said, Newton's method is iterative. That means once I have my first result, I can take this, plug it back into there, and get an even better result. So let's do that. So by Newton's method, the square root of 13 is 1/2 times 13 divided by, so now my guess is better than just 3, it's 11/3. 11/3 plus 11/3. So now we just have to do that arithmetic. All right, let's do that. That's 1/2 times. Well, we have 13 divided by a fraction. So when we have a fraction, we have to invert and multiply. So this becomes 13 over 1 times 3 over 11 plus 11/3. All right, squiggly. That's 1/2. 13 times 3 is 39. 11 times 1 is 11. So this is 1/2, 39/11 plus 11/3. And again, let's use our good friend, the butterfly method, to add those two fractions together. So the butterfly method says this should be 39 times 3, which is 90 and 27. That's 117. Plus 11 times 11, that's 121, over 11 times 3, which is 33. So that's 1/2 times 117, 121 is 238. Divided by, whoops, I missed my 3 there. 3 times 33, divided by 33. Now 238 is an even number, so let me cancel that out with the 2. So the square root of 13 should be approximately equal to, 2 goes into 238, 119 times. 119 over 33. So that should be a better approximation than 11/3. Well, let's see. What is 119 divided by 33? Well, I'm sure I just don't know. But 33 doesn't go in 11, but 33 goes in 119. Well, 3 times, right? Because 3 times 33 is 99. So let's subtract those. 119 minus 99, that's 20. Now again, I'm off in decimal territory now, because 33 doesn't go into 20, so I'll tack on a 0. Now 33 does go into 200. Well, how many times? Well, it's going to be 6 times, isn't it? So we've got 6 times 33 is 180 and 18. That's 198. Look at that. Subtract that. That comes out to be 0.2. Okay. Well, 33 doesn't go into 0.2, so I'll tack on a 0. But 33 doesn't go into 20 either. So that means I have a 0 up here in my dividend. So I need to tack on yet another 0. And we can see what's going to happen here. This is going to be 6, because 33 goes into 206, and that's just going to repeat forever. So after 2 iterations, 1, 2, it seems that the square root of 13 should be approximately equal to 3.606, blah, blah, blah. Well, let's get out our calculator and see how close we came. 13 square root. Well, look at that. According to my calculator, the square root of 13 is about 3.60555. Well, you could round that. So Like that. So we came within, 1/1000th of the actual value with just 2 iterations of Newton's method. So there you go. If you stuck around with me this long, well done. How to calculate square roots by hand using Newton's method. As always, thank you for your time and attention, and enjoy your lessons.